Hello again, Invisible class. What we're going to be talking about in this video is homogeneous systems. And I just pulled the first 4 homework problems from this section. And it's very similar to, you want to think about these as this, very similar to constant coefficient, homogeneous, linear ordinary differential equations. In that we do some auxiliary calculations, and then basically our solution looks like an exponential times some vector. But of course we have a repeated roots case and complex roots case and these sorts of things. So our first example is dy equals 2, 1, 0, negative 3 applied to 1. And keep in mind here the vector y stands for the functions y1 and y2. And rather than x's, I'm going to use t's as the independent variable now. Okay, so what we do is we solve the eigenvalue eigenvector problem for this matrix. So a minus lambda I is 2 minus lambda 0, 1, negative 3 minus lambda. Setting the determinant of a minus lambda I equal to 0, that tells us that 2 minus lambda times negative 3 minus lambda minus 0 equals 0. And once again, this thing is already in factored form, so we just write lambda equals negative 3 or 2. Okay, well now that we have our eigenvalues, it's time to find our eigenvectors. So, okay, well, let's just go in increasing order here. Notice, by the way, they're different real numbers, and that's actually the best possible scenario. If lambda equals negative 3, we get the matrix, let's see, 5, 1, 0, 0. The vector components I'm going to call v1 and v2. And as always, we're setting this equal to the 0 vector. We only get one equation from this. Well, we really get 2, but it doesn't tell us any information. We get 5v1 plus v2 equals 0, so v2 can be written as negative 5v1. Now when I go to write out my vector, v negative 3 is whatever v1 is, and then whatever v2 is, but v2 is actually negative 5v1, which means I can again factor out v1, get 1, negative 5. And if I let v1 be 1, I'm just going to get v negative 3 is 1, negative 5. So you just pick one of them out. It doesn't matter which one. For lambda equals 2, the procedure is similar, except this time we get 0, 1, 0, negative 5. And this leads to the equations v1 equals 0 and negative 5, I'm sorry, and v2 equals 0 and negative 5 v2 equals 0. Both of these tell us that v2 should be 0. So when I go to make my vector, v1 is free to be anything it wants, and v2 must be 0. Factoring out v1, I get the vector 1, 0, which tells us that the vector v2 should be 1, 0. So now I have my eigenvalues, I have my eigenvectors. How do I make this a solution? Well, the solution is the vector function y equals c1 e to the lambda t times the corresponding eigenvector plus c2 e to the different lambda t times the corresponding eigenvector. And that's it. So we can see that if we have distinct eigenvalues then it matches the second order constant coefficient homogeneous linear case almost exactly, except we have to find the corresponding eigenvectors as well. Okay, so let's try number 2 now. By the way, the distinct eigenvalue case is the good case. It's the best possible scenario. For number 2, we have dy is -1, 0 to -1 applied to y. And we just followed through the same procedure. We first find the eigenvalues. A minus lambda I is -1 minus lambda, 0 to -1 minus lambda. Setting the determinant equal to 0. We can see that, well, the 0 doesn't affect anything, so I just get lambda equals -1, and it's repeated. Okay, well, I still have to find the eigenvector corresponding to this, so we say, all right, well, let's see. If I plug in lambda equals -1, I get 0, 0, 2, 0. And the vector components v1 and v2, and again they're set equal to the 0 vector. This yields 0 equals 0, or 2v1 equals 0. If 2v1 equals 0, that tells us that v1 must be 0. Hence our eigenvector is v1, which is 0, and then v2, which is free to be anything that it wants. We're going to set it equal to 1 like we do almost all of the time. And so we get the eigenvector 0, 1. I'll remind you that we don't have to let v2 here be 1. It could be 7 or 10 or pi or something. Just it's easiest setting it equal to 1 usually. Now, what we do with the repeated root case, if we didn't get 2 different eigenvectors, then we have to solve an auxiliary equation, but it's not like the previous auxiliary equations. We need to solve A minus lambda I applied to some vector W actually equals V. In this case, we have A minus lambda I. That's going to be 0, 0, 2, 0. The vector components of W, I'm going to call W1 and W2. And the V is the eigenvector here, so 0, 1. So this is going to yield a system of equations. 0 equals 0, and then 2W1 equals 1. This, of course, tells me that W1 equals 1/2. So that W equals 1/2 W2. Now, what we want out of this W is to make it as easy as possible. And usually, setting quantities equal to 0 makes things easier. So we're going to take W to be 1/2 0. Now, once we have all of this information, we can actually just write down our solution. The vector function y is c1 e to the lambda t times the eigenvector plus c2 e to the lambda t times, and now we're going to get a combination of the vectors v and w. It's t times v plus w. And that's it. So the procedure is pretty much the same, but what we have to make sure of is that if we run into a repeated root, or a repeated eigenvalue rather, that didn't have distinct eigenvectors, we have to do this separate calculation and remember the special form of the solution. Okay. So number 3 is somewhat different. Yep, somewhat the same as well. I've worked these out in advance so that I don't make too many mistakes on the board. So we have dy equals 2, 1, negative 1, 2 applied to y. As always, we find the eigenvalues and eigenvectors. And to find the eigenvalues, of course, set the determinant of this a minus lambda I equal to 0.